Okay. Hello, everybody. Right. Let me start this up. Why does this sound louder than usual? Is the volume level okay? I feel like the game is louder than usual. Maybe that's just my sound is turned up louder than usual. Let me know if my voice is too quiet, though, in comparison. It should be okay, though, I think. Okay. There we go. Well, how is everybody who is listening? Greetings. Hello, Admiral Entropy. Nice name. Very physicsy. I'm just finishing my tea. Apologies. Tea is in the drink, of course, not tea is in dinner. You almost ended up doing your grad work there when Professor Boschia moved there? Oh, cool. Where are you? What department is that, Professor Boschia? Because of the lockdown, I've spent such little time actually in the department. I basically only know people in my research group, which is the theoretical particle physics group. Yeah, which are they like astro or cosmology or? Oh, he's not more in Los Alamos. Oh, cool. Quantum information. Ah, interesting. I have a friend who's doing a PhD here and there in the one of the quantum computing. Well, I think there's only one quantum computing group actually. I'm not sure, but they're in a quantum computing group here anyway. Let's vote for. So, where are you doing your graduate work then? I like desert hills. Oh, you did yours a long time ago. Ah, okay. Retired from physics except for fun. Ah, awesome. Yeah, I don't know how people that study physics ever stop doing it. Oh, bugger. It's too addictive to put it away forever. Wait, this isn't even a... Oh, you know what? I just realised. I didn't click on the CTGP tracks again. These are all just standard tracks. Damn. I'll change that after this one. Oh well. At least that means I know this track for a change. Oh! Okay. That was pure spite. That was pure stupidity. Oh, you did it at Yale. Oh, cool. I got rejected from Yale for a PhD. Yeah, it's lovely, that area though. Yale is in... That is in New England, isn't it? That sort of area. Yale, and they're all kind of East Coast. Yale, Harvard, MIT, those ones. Brilliant. Oh, cool. New Haven. Oh, right, yeah. Is that Connecticut? Is it? I can't remember. Yeah, Connecticut. Cool. I've only ever been to California in the US, but I would like to spend a lot more time there. Oh, what? That was poorly done. Okay, now I'm going to switch to the CTGP tracks. Because at least then I have an excuse for doing badly, which is that I don't know them. So what stuff, if any, has everyone been reading this week? What kind of physics stuff have you been looking into? If you've been looking into any, I don't know. Lots of foundational QM stuff. Oh, cool. What, stuff like, I don't know, Bell's theorem and things like that? That stuff is always pretty mind-bending. Speeding through ICRC proceedings mostly. What does ICRC stand for? International something Cherenkov. From your name, I'm guessing, is it something Cherenkov Ray something? I can't remember. It's taking a while to find a game. Oh well, once it's in one, it's pretty... Oh, a big cosmic ray conference. Oh, cool. Classical quantum correspondence, HJ equation, that kind of thing. Oh, right, interesting. Yeah, I've always found it pretty cool when you do these things to prove the classical limit of quantum mechanics. And you can, like, recover, you know, Newton's second law from the Schrödinger equation and stuff like that. I think that stuff is always quite neat. Oh, we've only got one person. Interesting. Ah, something tells me they're gonna beat me from their score. Let's go random. Oh, I think I've played this one before. Oh yeah, I'll read that in a second. Don't drive and derive. Oh wait. Oh. Wow, brilliant. I thought I had to go to the right. Oh my god, I'm going exactly the wrong way. Okay. I thought the exit was on the left, on the right, not the left. Bugger. I can already tell this is going to be truly appalling. For one thing, this person has like, what, a 9,000 VR or something. And mine is like 5,000. Oh, what? I didn't realise there was a jump there. Oh, stupid. Ooh, sorry, I was reading a message then. It's cool to see Schrodinger's motivation and basically the equation. Yeah, no, that stuff is cool. I think the way I've had it explained to me before, it's to do with you needed. I can't remember what the equation is that motivates it, but there's something that means you wanted a second derivative in space and a first derivative in time. And that was kind of the motivation for why you wanted the equation in the form it is, but I can't actually remember why it's motivated like that. Oh, brilliant. I'm trying to think why that is again. Yeah, it's I can't remember. Oh, fantastic. Omega equals a squared over 2n. Oh, right. That probably is it, yeah, like it, you know, it should have a wave solution, so... yeah. Well, isn't it like... You think about, oh, right, okay. I was thinking, like, you think about a... what, like a quantum harmonic oscillator or something, which has got energy roughly h omega. And so from that you have energy is proportional to omega, but then you also have energies, like you said, it's like k squared, or momentum squared. So to have those things agree, if you want it to operate on a wave-like solution, you need to bring down two lots of k, so that's a second spatial derivative. And then you need one derivative in time to bring down the omega. That's the basic way I'm thinking about it, which I guess is a little less technical than what you were talking about group velocity. Is this the same guy I'm racing that's got like the 9,000 VR? If I beat him, that'll be quite a lot of points I'll gain. Though that does seem unlikely. What's a standard candle? Oh, hello Tim. I didn't recognise your name until I read it. This is that user is my friend from my A-level physics class, and one of our other friends couldn't for the life of him remember the definition of a standard candle, no matter how many times we went over it. So a standard candle is something that's used by astrophysicists to be able to gauge distances. So it's a type of event where you know the sort of luminosity or the kind of total power this thing should give out. And then because the intensity you measure when you're a distance away from something is proportional to the luminosity it emits divided by the distance to it squared. So you can use it to work things out, like, you know, distances to well, I think type 1A supernovae are a particular standard candle. So if you see one of these going off in a galaxy or something, you can work out the distance to it by isolating the intensity from it. But our friend couldn't remember the definition, so he kept I think the definition was the luminosity of the known luminosity of a particular event, and he kept saying it as the luminosity of a known event or something. Yeah, exactly. It's just a source with a luminosity, you know. But like a Type 1A supernova is a good example. I think Type 1A supernovae, they're the ones where you've got like a binary system of a white dwarf and a red giant, and the white dwarf will sort of strip material off of the red giant until it reaches a certain critical mass that it's taken off, and then you'll get very sort of quick, rapid fusion in that outer layer that has been stripped off the red giant, and that creates a big burst that is a Type 1A supernova. And you can calculate, you know, using, you know, you can theoretically calculate the intensity of that blast. What am I you asked what am I working on for my PhD? I see it's particle physics. Yeah, it's sort of like the intersection of particle physics and cosmology is my rough area. So I'm interested in phase transitions in the early universe, particularly the electroweak phase transition, but sort of thinking about how this... Wait, where did that red shell go? Thinking about how this phase transition actually happened cosmologically, in terms of bubbles of the new phase after the electroweak phase transition sort of growing and nucleating, and then these bubbles can kind of collide with each other, and this produces gravitational waves, people think, and it's complicated. Yeah, it's complicated in that this is it's a strongly coupled system that these phase transitions happen in. Zooby-Doo says, nice character bite combo. Ah, thanks, Zooby-Doo. Yeah. Oh, you were thinking of a candela. Is a candela just isn't a candle just like a unit of luminosity? I don't know what a candela is. Or is that the same as a candle? Or is the unit candela? I can't remember actually. But I think that's just a unit of luminosity. Oh, it is, yeah. Okay. One of the most used SI units. Yeah, very standard. Oh, I didn't check the name of this one. I still don't know what this one is. Why do I keep missing the boost as well? Actually, Zooby-Doo will be able to tell me this. When you get the boost in Mario Kart Wii, is it where you hold it down like just before it gets to 1 second, and then hold it from just before 1 second, or is it you press it on like when it goes go? Exactly. I can't remember if it's the same or if it's different for Mario Kart 8, because they kind of vary. Just after 2. Okay. Thanks, Tim. I mean, Lead Fence. Dang. Oh, what the? Flip. Wait, where is the start line for this thing? swear I've already crossed it twice. Do you have to do calculations in QFT and curved space-time to figure these things out? Yeah, that's exactly it. So, under my face. I don't know what you mean, Tim. Yeah. So, the model I'm looking at it in is this Randall-Sundrum model, which is a 5D model for the universe, where you've got two brains. One is the brain where all of the standard model fields we see around us are, and then there's another brain that gravity sort of localizes to. Although gravity can move in all 5 of the dimensions. But anyway, you have to stabilize the size of this extra dimension. So in doing that, you have to put a scalar field in, or adding a scalar field into this setup is the sort of most basic way of doing it that Goldberger and Wise did back in the 90s. So yeah, so that's a scalar field that's coupled to gravity in this system. And if you want to fully solve the geometry of this system, it's quite difficult. So the geometry of this Randall-Sundrum model, it should be sort of ADS. It's supposed to be a kind of a slice of 5D. Oh, I was disconnected. Okay, oh well. A slice of 5D anti-de Sitter space. But when you add a scalar field in to stabilize the size of this extra dimension, which you do have to do, there's a back reaction from it, because of course the scalar field has, it has an energy momentum associated with it. It has a stress tensor term to it. Well, I mean, as in it contributes to an overall stress tensor term, and that has a back reaction effect on this metric. So solving exactly for the metric, scalar field coupled system is quite difficult. Yeah, and to calculate things like the tunneling rate, so the rate at which these bubbles of the new phase nucleate, you need to know what the metric is. And it has there's an effect on it from the presence of this scalar field. So that is all a calculation in QFT and curved space, yeah. Sounds easy, you just finished it. Oh, thanks. You've done my PhD for me, great. Yeah, and people have done quite a lot with it in certain approximations. So of course you can ignore the back reaction effect. You can just say that the scalar field has no effect on the metric. But then when you do that, when you calculate things like the mass of the scalar field that you have to put in to stabilize this 5th dimension, you get a totally incorrect mass for it. So it is important to include it. And you can do numerical things on it, of course. You can study things in certain limits, but it would be interesting to see if you could solve it analytically. And we're trying to do that. Well, we're thinking about doing that using holography in some way, because this Randall-Sundrum model, it has an interpretation in holography, which, if you haven't heard of holography or the ADS-CFT correspondence, it relates theories in D plus one-dimensional anti-de Sitter space that include gravity, usually string theories, generally, to d-dimensional conformal field theories. And this has lots of useful properties, particularly when one of these theories is strongly coupled. The dual theory is... Exactly, it's a duality, you're quite right. The duality also means that when one is strongly coupled, one is weakly coupled. So computationally it can be quite useful. Lewis, the aforementioned standard candle expert. Oh, I didn't realise you could hit those things. The Goombas. Dang, I mucked up that drift. Should have got that mushroom. Mathematica or Maple? That's the real question. Well, my supervisor uses Maple and I use Mathematica. That's my preference. But I mean, to be honest, I'm not particularly proficient in Mathematica, actually. It's something I used. I picked it up on a research project I was doing the summer before this summer. And I used it a lot then. But I did really badly then. But I haven't really used it since. So I'm quite rusty with it, and I never really learnt it from the ground up. It just kind of I used it for what I needed it for. So I should really study it more. Theoretical Phys 77. Hello, Theoretical Phys 77. Do you use any kind of programming in your research, or is it all pen and paper? Yeah, no, I do use like Admiral Entropy was asking as well. I do use programming. I think pretty much every physicist. You know, even if you're doing you know, very high theory stuff, you know, Mathematica is really useful. So I spent the summer before last, I spent at Caltech working on high energy physics theory paper in the maths department, and that was completely, you know, calculation. There was no approximation. It was pure conformal bootstrap stuff, and we used Mathematica a lot for that, to handle these sort of, you know, symbolic manipulations. So it's fantastic. Lewis the Gamer, can I have an update? If any of my mods are watching, someone ban Lewis. But yeah, so even if you do, you know, very pure theory kind of, not at all dirty, completely pure, unapproximated stuff, using Mathematica is still, or you know, one of these symbolic things is still really important. And I also use MATLAB too. You know, I do some numerical stuff. So at the moment I'm trying to do some numerical stuff with this scalar field gravity system, just to kind of convince myself of what's going on with it. And I was doing some stuff earlier on in the year numerically too, where it was again in this Randall-Sundrum model, so this 5-dimensional warped model. I was trying to work out wave functions for fermions that exist in this 5D bulk. Oh, what? How do you even get around this bit? Okay, bye-bye lead fence. Yeah, no, I don't think Mathematica is taught as much. Certainly not as much as things like MATLAB or Python, which are pretty standard. It is weird how it's not taught, really. I guess maybe the reason they don't teach it is possibly because tutors are worried that their undergraduates will just use it to cheat on their homework. You know, if you're doing a general relativity course, there's a package in Mathematica which can calculate all these Christoffel symbols and stuff like that for you. But of course, unless you sit through and do the hours actually working through it yourself when you take a GR course, you probably don't ever really know GR. You know, you have to suffer a bit when you're learning physics, particularly GR. And if you just knew Mathematica, you could just get rid of all that suffering. So maybe it is a strategic choice by university physics departments. I don't know. Yeah, using Mathematica to calculate the tip for dinner is a little. That is a definite flex if you did that. Yeah, no, I think probably it's the same for most people. I don't know of any people that I've spoken to that took a course in Mathematica. Certainly not an undergraduate one. So I guess it is just something, you know, you pick up as you do physics long enough. Yeah. Oh, I wasn't looking where I was going. Bugger. Double bugger. Oh, these mushrooms are so stupidly placed. Oh yeah, yeah. Figuring all that stuff out is pretty horrible. That's probably what I'm gonna. So I'm doing a thing on Saturday where we're gonna talk about Mercury's orbital precession, and that's going to include implicitly doing some stuff like that with the Schwarzschild metric to derive this result that Mercury precesses its orbit. And I'm contemplating how much to actually show on the stream of what goes into the result, because I don't think it's too entertaining for people to just watch, you know, watch for an hour me working out Christoffel symbols and probably making a dozen numerical errors. But oh, what am I doing? I thought it went left there. Yeah, there is I can't actually remember the name of it now, but there is a good GR package. I mean, there's probably a few that can calculate things for, you know, you input your metric and then it can find you all of these Christoffel symbols and stuff. That's this Saturday. That is what I'm calling the Saturday spacewalk. So the idea is just I'm going to go and talk a little bit about a few different planets and stuff in the solar system, one by one, and then probably also black holes and stuff too, and stars maybe in general. But for the first one, obviously Mercury is the first planet, so we're going to talk about Mercury and going to try and derive from GR the result about Mercury's orbital precession. So that'll be on Saturday at 7 PM. I don't like this map. I don't know what it's called, but I don't like it. Oh, I just realised I didn't actually change the name of the stream. So this again, this says science and technology, and it says Friday office hour, but this is not Friday office hour. Lewis the Gamer did some coin thing. I don't know what that means, Lewis. What the... Thank you, I think. I haven't actually looked into half of these things on Twitch and what they mean, but I assume that those little gem thingies are a good thing. You donated bits. What does that mean? Such a badass. Oh, thank you. Yeah, I really need to change the name of the stream. You think you get money? You paid money to do that? Why would you do that, Lewis? 1 bit costs 1 cent. Whoa, Lewis. Spending a whole $1 on me. You're spoiling me, Lewis. Okay. I'm going to quickly try and change the name of the stream because it's wholly inaccurate. How do I do that? Okay, there we go. I'll just click OK. Because at the moment the category is totally inaccurate. And this should be under Mario Kart Wii. Okay. Oh, I'll go random. Okay, there we go. That should be corrected now. Excellent. Back to actually racing. 'Cause we like you, Mr. Streamer. Oh, thank you. Lewis is just... I mean, Lewis the Gamer 1996 is just flaunting his big bucks. Because he decided not to go to university and got a job and earns a lot more money than I will ever earn. As a theoretical physicist. Damn. I was talking to one of my friends the other day, who's also a theoretical physics PhD student, and we were talking about diversifying our research to make it slightly more employable. As in employable in like a university context, as in like... What the? Because obviously some kinds of research are more fashionable at other times that, you know. And so I was thinking about other kinds of fashionable theoretical physics research to maybe make it easier to get a job, and I was talking about dark matter stuff and gravitational wave stuff as well, which I do a little bit on, but not really much in about actually detection or computing these things, really. Um, and then we kind of came to the conclusion that theoretical physics and employability are kind of oxymorons. Um, oh, and just accepted the fact we're probably never going to get jobs. But you know, job isn't everything. I don't get this track. Is it a volcano or is it ice? Or is it both? Oh, some of these custom tracks are just a little too challenging. I mean, I'm also not very good, so that doesn't help, but like... Oh, this is starting to frustrate me. Who needs real food when you can think about it? Exactly. Who needs food when you have theoretical physics? Not me. Okay, I have no idea where I'm going now. Okay, apparently that worked. What the What is this fever dream? You can work in industry. Think tanks don't care so much what your thesis was about. Yeah, no, I can imagine that. I mean, I guess if you're going into something like finance or a think tank or whatever, they're not really going to care whether your PhD was in dark matter research or, I don't know, extra dimensions. Well, you know, those do have similarities, but I mean, phase transitions or dark matter, I guess. They probably won't care. Yeah, I really don't like this track. I can't actually tell where on earth I'm going on it. Okay, it ended. Or did it do the thing where it crashed? It has crashed entirely. Excellent. It does it usually at least once, generally around twice whenever I stream. Because the CTGP mod is it's not a proper Nintendo licensed mod. It can be a little bit janky. So I'll just restart it. That's fine. Thank you for the Fs. Thank you for the rip. Well, green, purple, and white. Yeah, I haven't really thought about what employment-wise I might do after my PhD. I mean, at the moment, it would be nice to do a postdoc and kind of stay in that area, but obviously it's so competitive, that can be difficult. But we will see. Time is relative. I just missed that comment. I don't know what it was in relation to. Advisor should help you find a postdoc when the time comes. Yeah, I hope so. Have you heard of geometric algebra? I've heard of algebraic geometry. I don't know if that's the same thing or if geometric algebra is a different thing. But I mean, I don't know. I don't really know anything about algebraic geometry anyway. When Labour win the next general election, you'll get a house and free food the rest of us will pay for. You say that like it's a bad thing, Lewis. No, they're not the same. Okay. What's the difference? What's geometric algebra? Moving to Canada. Oh, right. Yeah, I know a little about Clifford algebras and spinors. I've never heard it called geometric algebra, though. I guess I've probably not studied these things in a very mathsy way, in a much more physicsy, you know. Okay, bye-bye, Lewis. But yeah, what do you mean by geometric algebra, Eddie Astorius? Sorry, I might read that name wrong. What does that? Okay, Lewis is doing something. You saw a quick introduction on YouTube. Okay. But yeah, no, sorry, I haven't heard, whatever it is, I haven't heard it by that name. Okay. Now, I'm sure by half 8, it's definitely going to break at least one more time. It usually breaks twice. It's never broken more than twice, and I think it's probably only once broken less than twice. So we will see. Oh, those are cool item boxes. Oh, right, okay. Oh, yeah, so that is how Theoretical Phys 77 described it. Okay, no problem, Admiral Entropy. Enjoy your meeting. Yeah, okay, great. See you on Saturday. How do you think of spiders? The flagpole? Yeah, the flagpole analogy is pretty good, where it's, you know, like a kind of like a vector that has orientation. But yeah, spinners are a difficult thing to picture, to be honest. Yeah. But yeah, the flagpole analogy is quite good, where it has an orientation. I mean, sorry, it has like a, you know, a direction and also an orientation to it. But I mean, really, spinners are quite formal things, and I wouldn't at all say I know enough about the kind of geometry of them as I should do. More kind of the sort of representation theory side of them. Oh, did I click? I feel like I accidentally clicked the... Oh no, I didn't. No, this is the custom track one too. Okay, have a good dinner, Zooby-Doo. Oh, damn it, I forgot this bit slows you down. Yeah, when we were learning about spin and spinners in our second year quantum mechanics course, our lecturer did this really interesting thing with a scarf about, because, you know, spinners have this funny property where they're not, if you rotate them by 2 pi, you don't get back the same thing you had before. You have to rotate them by 4 pi to get back where you started with them. And he did this thing with a scarf where he knotted it in some funny way. No! Oh, and he showed that it was 4 pi periodic. You can do it with... when I finish this race, I'll show you how you can do it with, like, your hand. You can show that you can make your hand, like, move in a kind of 4 pi periodic way, if I can remember how you do it. Oh, have I seen Eric Weinstein's video where he talks about physics? I've seen a few of them. I'm pretty sure he did his PhD. Did he do his PhD in Oxford or something? Maybe he didn't. But anyway, he was like a pretty serious, physics doctoral student, and then I think now he works in finance or something, and does podcasts. Oh, he did it at Harvard. Okay, he's friends with Marcus. Is that Marcus de Satoy? But yeah, the thing how you can rotate something. How is it you do it again? It's something like what is it you do where you have to keep it upright and you rotate it twice. So it's like that's so many degrees, then it goes around like, no, that's not right, that's going to turn it upside down. I can't remember how you do it actually. Well, it's the thing where you rotate it by 720 degrees. Is it like, I can't figure out how to do it with my hand. There is something to do with rotating the wrist. It's like you bring it under. Wait, so there it's like facing forwards, and that's 180. No, I can't remember. There's some funny way you do it. Oh no, wait, don't you bring it over? Is it over? Is it like? No, this just looks really weird. There's something you do that's funny to it. Where it's like... Oh yeah, that was it. That's it. Yeah, so it's forwards, it goes around, that's 360, and then under, that's... Oh wait, I'm sorry. I'll do it after. I remembered how you do it now. Yeah, it's over, not under. Unless you could bend your elbow in a ridiculous way, you couldn't do it under. Oh, excellent. Oh, these item boxes are different. That's cool. Oh, brilliant. Wow. Oh. What? Oh, okay. That wasn't so bad. Why is my thingy stopped to me? Okay. Now it's back. Oh, I wasn't bloody looking. How does the flagpole show the 720 trick? Yeah, I'm not sure the flagpole analogy kind of explains it fully in that way. I don't know. I'm not actually sure, to be honest. Yeah, I don't know. Geometrically, I'm not sure if it does make sense. I mean, algebraically, it's totally okay. If you rotate the spinner, you get minus the spinner minus itself when you do it by 2 pi, and you get the same thing back when you do it by 4 pi. But I don't know how to understand that in terms of the flagpole way of thinking about a spinner. Maybe it's obvious, maybe you can do it, I don't know. I'd have to think about it. Yeah. Excellent. But yeah, the thing where you rotate it by 4 pi is like, so there the handle's facing forwards. Then you can go, that's 180. That's 360. Then that's another 180, and then that's 720, and you do it without putting the cup upside down. I don't know. That's some weird analogy for. I mean, it doesn't help. It doesn't actually explain it. Obviously, it's just a. I don't know. It's like something weird our lecturer did at the time. where he showed how this thing can rotate by 2 pi. Oh, I was disconnected. There's a cool GIF you can see on Wikipedia, I think, for the Wikipedia page on spinners or something, that shows like loads of them attached to a cube kind of rotating, which is a pretty trippy looking animation. Searching for players. Are you a physics student? Theoretical Phys 77? I mean, I guess your name is kind of suggesting that you might be. Spinners in year 2 QM. You used to study physics. Okay, cool. We didn't really do spinners in second year quantum mechanics. We only really it was just kind of a side comment on them. I mean, we did sort of simple spinners in how you do them in like studying this what's it called, the Stern-Geller experiment. Not spinners as in proper spinners like in QFT or something. Just very vaguely in second year QM. So like if you were calculating things like if you polarize a beam of electrons in the Z direction or something, and then you want to find the probability of measuring the spin of the electrons in an angle in a direction at some angle to the Z direction, some angle to the direction you polarized them in. Well, not polarized, but that you prepared their spin in. So just simple calculations like that. Well, I mean, not simple calculations, but calculations like that. I think Binny's book was one of the recommended ones, because Binny was the lecturer a few years that we did it, because my lecturer for this was Blundell in Oxford for my second year. But Binny's book was recommended, but I don't know, it wasn't my favourite book on quantum mechanics. I can't actually remember which my favourite book on QM was. I think Griffith's book on quantum mechanics was quite good. I remember reading that quite a bit, especially for stuff about spin. I mean, Griffith's, just comes to save the day for a lot of things. His EM book was really good. His particle physics book was really good. His book on elementary particles. And yeah, his quantum mechanics book is good too. Binny's book just seemed kind of too, I don't know, it seemed a bit too formal in places, that it was a little hard to read. I'm not sure. But the lecturer himself was really good, so we didn't have to rely too much on a textbook, because the lecturer was really good. Griffith's book didn't use too much bracket notation. Okay, I can't actually remember now I think about it. This was... When/how did we learn? Well, I learned that in that lecture course in my second year. I don't know, I can't remember how much is in Griffith's book, because it's been a while since I looked at that textbook. But yeah, I learnt it in that second year course. Bracket notation. I mean, it's pretty... I suppose if you've studied linear algebra before you come to study quantum mechanics, then the notation is not really that surprising. It's just, it's just a vector space and the dual to that vector space. So the notation kind of follows on pretty much from vector space and inner product notation. But yeah, it was in that second year course we studied it in the context of quantum mechanics anyway. Ooh, almost hit the wall. This must be like a proper course, like one that's from another game, because it's not designed completely crazily. It feels like one of the old Game Boy or SNES tracks. Oh dear. Oh, okay. Did I take any pure maths courses during my undergrad? No, not really. I mean, the undergrad course, the undergrad course at Oxford is pretty restrictive. I mean, in a good way, in that we don't really get to choose any major modules and stuff until our fourth year. You know, all of the core modules are the same. Well, I think now actually they've changed it a bit. Now you do get some choice in your third year, but when I did it, we had to do all of these different things that there was no choice about in years 1, 2, and 3. So there were no real pure maths modules. I mean, we did a bit of, well, we did quite a lot of linear algebra in first year, and then we did some complex analysis as like an option you could do. Well, I did it in first year, but you could do it in any year you wanted. And then in my fourth year, because the fourth year was hosted jointly between the maths department and the physics department, I took a sort of group and representation theory course then, and I went to some lectures on, well, I did another one on like complex analysis, and then I attended some lectures on one on manifolds too. But that was it really, in terms of more, purer mathsy stuff. I never really did any, topology, and I wanted to do topology in my second year, because you could choose to do it in the maths department, but I think my tutors were not keen on us taking modules from other departments, and it needed their permission, so I didn't do any topology in the end. I did consider part 3 actually. I sort of thought about it, but I think the difficulty would have been funding, because the course I did, so my fourth year in Oxford, although it was like a separate course, so it wasn't part of the bachelor's in physics, it's you change courses onto it, the Master of Mathematical and Theoretical Physics. It still, for funding purposes, is counted in the same way as the integrated masters, so I didn't need to apply and get extra funding for a master's, whereas if you change university, then you have to graduate in your third year, and then you do need to get different funding for your master's, so then it's postgraduate funding, and that's nowhere near as simple as normal student finance undergraduate funding, so it wouldn't have been possible for me to fund to do the part 3 anyway. And the MMath Phys and the part 3 at Cambridge are actually, they're very similar. I mean, part 3 is a lot older, so it's maybe got more of that prestige to it. I think the MMath Phys is only about 5 years old, really, so it's quite a young course. And it's kind of weird that it took Oxford so long to do a course like that. It seems bizarre to me anyway that it was such a long time coming. But yeah, I think they're pretty similar, so there wasn't much in it thinking about it, really. Did I do any group theory prior to fourth year? No, not really. We didn't do any courses in it. but I'd sort of read about it on my own. A really good book actually for sort of looking at group theory in physics that's quite easygoing is this book by Jacob Switchenberg called Physics from Symmetry. And that's a pretty nice book that goes into, you know, some representation theory and group stuff and applies it to, you know, field theories and QFT stuff like that. Yeah, it is a really good book. And then obviously there's also the classic, the Howard Georgi one, the, what is it called? Is it Lie groups in particle physics or just group theory? I can't remember what it's called. But the Georgi one is also a classic. Lie groups in particle physics, okay. Yeah. Oh bugger. Yeah, but one of the books that was recommended for this course that I did in my 4th year, I can't actually remember what it's called now. It is called something like Representation Theory, and I can't remember who it's by, but it's a very heavy representation theory book. Obviously way more heavy than I think is probably needed for the sort of physics I'm interested in. And that was totally impenetrable. I could, you know, in order to read one thing in it, you had to know about 15 different corollaries and 12 other theorems and lemmas and whatever, and it was just totally impenetrable. But obviously it was thorough, but I never really managed to make any use of that. Voigt has a good one. I haven't read that one. Yeah, I've not heard of that. You did group theory in 3rd year and it was such a steep learning curve. Oh, Springer gave it free during the pandemic. Oh, I didn't know that. Is that on like the Springer link page or something where you can access all of these books if you have a login or something? Is it still free, do you know? Because that is a really good one. And if it's free, that's even better. Yeah, I had to buy it too. I bought it. I think I've got the first edition of it. I think the second edition came out pretty soon after I bought the first one, because the book, it does have quite a few little errors in it. I mean, none of them I think are particularly important, but I've heard the second edition is quite a bit better. Could it be? Could I come first? Nice. So was that the only good book I used? No, there was, well, yeah, so there's the Switchenberg one. There's, Lie algebras in, oh, it's Lie algebras, not Lie groups. Lie algebras in particle physics, the Howard Georgi one. That's a good one. I think Weinberg's QM book, Weinberg's QFT book, the first volume has quite a lot on groups stuff as well, applied to QFT. And I think that was quite handy. Yeah, I can't remember any others now I used. I don't think I did use any other books. Why is my right ear exposed? It's, well, there's no real reason. It's just because I like to hear things, but I also like to hear... I find if I wear a headset, I can't hear my own voice, and then I end up talking at weird volumes. So I always have one ear off just so I can more naturally hear my own voice, but I realise it does look a bit odd having one ear exposed. So apologies. But yeah, we mainly use lecture notes. There are some good lecture notes actually. There's oh, they're all saved now. I can't remember who they're by. What I'll do is I'll try and remember to link the lecture notes in the footnote of this video when I upload it to YouTube for later reference. But if I forget to put them in the link in the description, do just let me know. Or actually, alternatively, what you can do is if you type in !Discord into the chat, you can join my Discord, and then you can just remind me, and I'll just post them in the Discord. Like I linked some of my undergraduate GR notes the other day after a stream, because someone was talking about those. So yeah, so if you join the Discord, I will happily just send you those lecture notes. Flip. Oh wait, actually, I just remembered you're already in the Discord, aren't you? I forgot. Theoretical Quiz 77. Yeah. Sorry, my memory's really bad. Because I'm just kind of quickly glancing, I sort of forget who's sending which message, and then, yeah. But yeah, I'll put those lecture notes in after. But if anyone else that, other than you is watching and wants to join my Discord, then please do feel free. But actually, the group theory notes I was thinking about, they are sort of quite heavy. They've got a lot of this kind of, oh, for goodness sake, a lot of this sort of root weight decomposition stuff, which I always found quite difficult to get my head around, to be honest. And like the Dinkin formalism, which is interesting, but also quite, you have to really look at it for quite a while, I think. Or I did anyway. It might be easy, probably easier for other people, but I had to study it quite a lot to get it. And then I think I forgot it all anyway, because I didn't use it after that. Oh, the offer from Springer expired. Oh, damn. Oh well. I don't think it's too expensive a book. As far as physics textbooks go, I think it's probably like around the £25–30 mark. So it's not too extortionate, but yeah, I mean, it's also not too cheap. But you know, as all of these things, you can, not that I would condone such a thing, you can usually find copies or very similar lecture notes online. But you should always buy textbooks, of course. Oh, damn. I was trying to hit them. Oh, what? Oh, at least I took them down with me. You just barely learned enough to pass the exams. To be honest, that was probably me too. Yeah. I got very done with exams towards the end of my degree. Just fatigue after what, like a, I don't know how many years, 7 or 8 years of exams every single year is quite tiring. Okay. Yeah, well, there are lots of good things where you can learn about Lie groups and algebras. Probably the Switchenberg book, the big blue one I was showing, is probably the nicest one to read. I don't know, I'd call it like bedtime reading, because it's not sort of a rigorous textbook, but if you read it, you can pick things up quite nicely from it, and it's written in quite a readable way. Yeah, he's quite good as well with doing, you know, explicit examples with like he does SO2 and U1, and then he does SO3 and SU2 and stuff. And it's quite nice to see all of that stuff done in full. Oh, I think I know this course, Shy Guys Market, actually. Oh. I didn't realise this was an actual track until I was playing Mario Kart 7 the other day. I assumed this was just a custom track, because I think it's just one I've forgotten that was in Mario Kart 7 completely. Damn. Oh dear. What? I forgot there was a jump there. Oh, you bugger. Oh, that was a blue shell. Nice. Wow, how many blue shells are there? Like, that was like the 4th one or something. Ugh. That was frustrating. Oh well. That full vector approach. Oh, do you mean for the collisions, for the threshold energy, where you had the 2 photons making a matter-antimatter pair? Oh yeah, that was the kind of, we did that sort of approach, I think, when we first learned special relativity. Our lecturer sort of emphasized 4 vectors, but she kept sort of oddly saying, which we used to laugh at quite a bit, 4 vectors are your friend. But she sort of said it in a bit of a funny way. I don't know. It made us laugh anyway. But yeah, they really emphasise using 4 vectors when we were learning special relativity. Yeah, the approach using 4 vectors is really nice. I mean, it simplifies the calculations a lot, I think. And it's quite a natural way to think about it too, because you can think about it in analogy to conservation of momentum. You just have this 4D version of momentum, which includes in it energy conservation. And it's a good habit, I suppose, to get in when you start learning relativity, when you start doing more in relativity, like when you start studying electrodynamics, like within special relativity. And then you've got, instead of an electric and a magnetic potential, you've got a 4 potential, which includes both of those. Oh, I wasn't thinking. And all that stuff anyway. But yeah, thank you for saying it was a nice approach. Well, I mean, why would I say thank you? It's not like I invented the approach. But yeah, it is a nice way of doing those problems. For special relativity, I think, especially for 4-vector stuff, I think Steen's book, Relativity Made Relatively Easy, is quite a good book. I think that's by Andrew Steen, Steane, as far as I'm aware. And I can't think what other books I used for special relativity. I think actually David Morin's Classical Mechanics book has some chapters at the end on special relativity that I seem to remember finding useful. That's yeah, David Morin, Morin, his book on classical mechanics. And yeah, I can't think of any other SR books off the top of my head. But yeah, Steen's book and Morin's books both have some good stuff in. Do I use French? As in, do I speak French? No, I don't speak French. Oh wait, you probably didn't mean that. You probably meant a book whose name is French. If so, I haven't heard of that book. Well, I also don't speak French, so whichever one you're asking, the answer is no. French AP. I don't know what that is. Is that a textbook? Oh, you stupid. AP French. No. I'm assuming that's a relativity text. Oh. Has it died? It always does it at least twice. I knew it. Okay. I will restart it again quickly. Thank you again for the F. He wrote a book on vibrations and waves, SR, etc. That doesn't ring a bell. No, I don't think I have used that one. I'll be honest, I didn't use too many textbooks actually. I generally tended to use lecture notes instead of textbooks. Unless the textbooks were sort of really highly recommended or really readable, I did generally just use lecture notes. Okay. Right. Yo. Hello, Velocity Fright. Hello, hello. You caught us just as the thing broke for the second time, but it should come back on now. Whoa, that's a cool purple. Okay. Oh well, it's all good. But yeah, definitely remind me to post those group theory notes in the Discord if I forget, because I might forget. I'll try and do it as soon as I come off here. But in case I do, don't be afraid to remind/nag me. Okay, let's see if we can get 2 more races in before it breaks. Well, I mean, it won't break again. It's never broken more than twice, so I think it's okay from now on. But let's just try and do 2 more anyway. Okay. Oh, at least it found a room a little bit quicker this time. I feel really self-conscious about my one exposed ear now that someone's mentioned it. But yeah, it is purely for purposes of hearing my own voice. Because I feel like it's weird talking while you can not quite hear yourself. But yeah. Safety purposes, exactly. Yeah, if there was a... Actually, yeah, I did have a fire alarm yesterday. And I had my headset on. I was listening... When I work, sometimes I listen to, like, ambient noises of Star Trek ships, which are kind of weird. I listen to, like, ambient Enterprise D bridge noises while I work. And I had those on quite loud. And the fire alarm went off, and it took me, like, probably long enough that I... You know, if it was a real fire, it would have been not advisable to realise the alarm was going off. But yeah, I think it's avant-garde too, actually. ABC 1, maybe ABC 1. Oh, like ABC 1, 2, 3. Oh, I get it. Like you know, like the Jackson 5 song. Well, or just like, not necessarily the Jackson 5, I guess. But yeah, hello ABC 1, 2, 3. Luigi's Island. Do I know that one? Oh yeah, I think I do know this one. Oh, flip. Get out of the way! Ah! Don't throw a banana at me. How do problem sets work in Oxford? Do they give you solutions, or does it depend on the tutor? I actually can't remember. I'm pretty sure they didn't. I think they didn't give us solutions. Maybe there were 1 or 2 where they did give us solutions, but I think for the most part, because the lecturers set the problem sets, and a lot of the problem sets are, you know, recycled for decades and decades, they don't want the solutions being released and then students just don't have to do any work for the next year or something. So I think generally the tutors are told not to give out the solutions. Certainly that's how it works for exams. The past exams, they were always very secretive about mark schemes, and we were never allowed to look at them, which was pretty, I don't know, pretty nasty. Because I think most places you would have access to like the last couple of years of exams, and you could see their mark schemes. But we had access weirdly to like the last 30 years or something of exams, but we weren't allowed to look at any of the mark schemes. So it was pretty pointless having all the exam papers. because you still couldn't look at the answers to them. I mean, I guess it's lots of practice, but like, you could have just answered all of the questions totally wrong and you wouldn't necessarily know. Yeah, we just had to figure everything out on the problem sets. I mean, the problem sets, you know, some of the questions were, you know, straightforward and you could find them in textbooks and stuff. But yeah, for the most part, they were designed to be fairly tricky. The problem sets were always more tricky than the exams, though. So, you know, it was supposed to be hard going when you were learning the stuff. But then when you come to do the exams, it's a little bit kinder. And also, wow, my VR's gone down like 300 just today. That's quite bad. Oh well. Oh cool, you're at Imperial, nice. IC is Imperial, isn't it? Imperial College. Let me know if I got that wrong. And they gave you the solution to the problem sets. Oh, right. Presumably not until you'd done them, though. So, I mean, you still had to, you know, figure everything out from the beginning. Yeah, Imperial is, I mean, pretty intense as well, I think, isn't it? In terms of problem sets and stuff. I've heard Imperial is quite hard going. Oh, what, they gave you the solutions as you were doing the problem sets, or like they were alongside? Oh, okay. I think the different... Oh, no. Rats. I think the difference is the reason our problem sets were quite tricky is that we didn't have... I know a lot of universities have exams sort of in January time or something. As well as exams in the summer. But we only ever had exams in the summer, so I mean, we didn't really have any assessed stuff. And your problem sets never counted towards your overall grade. So, you know, technically you could just arse around and not turn up for anything, and they might not sort of realise you were going to fail until the end of the year when you actually failed your exams. Though obviously they did pick up on it sooner because of the problem sets, so you still had to complete the problem sets. And they were allowed to be kind of mean with them because they didn't actually count for anything graded. Oh, I see. Yeah, ours was all exams too, really. We had a few kind of assessed practical things where you had to go and describe an experiment you'd done to some lab demonstrators, and then that counted towards a mark. But it was like such a tiny amount. Basically everything we did was just on exams. Oh, yeah. That's... oh well. We're doing badly, but who cares? We're probably not going to finish. Because this is the third lap. I think I'm going to have to start playing this off of the stream just to kind of recoup some of the VR I lose when I actually do stream. Oh, can we get not last? Way, not last. Sweet. That's good enough for me. Okay, well, it's 8 o'clock, so, I mean, it's 8:30, so I'm going to leave it there for this evening, but thank you very much, everybody, for for listening. If you want to join my Discord, you can find that in the chat if you type in !Discord. But yeah, if not, I'll see some of you tomorrow for my office hour, and I'll try and remember to I'll try and post those lecture notes in my Discord now. But yeah, thank you very much for joining, everyone. Okay, see you later. Bye.